All right, in the generalized linear model, we assume that we have an exponential family distribution, and this is what the exponential family distribution looks like. In the previous video, I showed that the mean of that distribution, I showed how that is equal to the first derivative of this function b with regards to theta. And so now in this video, I'm going to talk about the variance of this distribution, and I'm going to show that it is the second derivative of b times a of phi. Okay, and this is just another notation where I've written second derivative with regards to theta instead of using that prime notation. Okay, but this is the same thing twice. All right, so how do we show this? First, I need to show that the second derivative of the log likelihood function with regards to theta this equals the negative of the first derivative of the likelihood function with regards to theta squared. Okay, and this is actually a property of score functions, regardless of the fact that this is the exponential family distribution. This is something that we know about score functions. Okay, so how do but let's go ahead and just show this for the sake of completeness of this proof. Let's show that this is true. Okay, so let's start with what is the expected value of the second derivative of the likelihood function with regards to theta. The likelihood function is going to be the log of my distribution of y. I'm just going to write fy as opposed to writing fy theta phi, right? But this is basically what I'm just going to call it fy here. Okay, being a little lazy on that notation there, but you can see what it is, right? So first, let's go ahead and find the first derivative. So second derivative is the derivative twice, right? So I'll leave one derivative out, and then I'll go ahead and take the first derivative of log of fy, right? The derivative of a log is 1 over f times the derivative of f, right? That's basically how you take it's like a chain rule for derivative of a log. Okay, now let's take the derivative of this, and now I have a product, so I'm going to need to use the product rule. I'm just taking the derivative twice of a log of a function. So first, let's go ahead and take the derivative of the first term, and so that'll be negative 1 over fy squared, okay, times, so basically I need to use the chain rule to find the derivative of 1 over fy, so that'll be the derivative of fy, okay, and so that's the derivative of this first piece, times the second piece, which is just this guy again, so I can go ahead and just square it, plus the first guy times the derivative of the second guy, right, which is just going to be the second derivative with regards to theta of fy. Okay. All right. Now I can go ahead and I have an expected value of a sum, so I can break this up. I'll go ahead and pull out this negative sign. The expected value of 1 over fy squared. Actually, since they're both squared, let me just write 1 over fy times, and then let me square it. Okay, so since they're both squared, all right, plus the expected value of 1 over fy times the second derivative of f with regards to theta. Okay. All right. So this second piece here, this is equal to 0, which it's similar to when we were showing this proof here. We showed that the expected value of the first derivative of the score function is 0. Well, so is the expected value of the second derivative of the score function. So let's go ahead and just show this. This is going to be the integral. It's the expected value with regards to f of y. So you would write f of y, and then whatever you're taking the expected value of. Okay, dy. So these pieces here cancel, and I'm left with the integral, the second derivative. Okay, since the derivative is with regards to theta, I can pull it out. Okay, and this piece here is 1. So I'm taking the second derivative of a number, of a constant, which is just going to be equal 0. So this piece here will basically go out to 0. All right, and then this piece here, this is the same as this. So let's show that. So just as like kind of a side note. Okay. The derivative with regards to theta of log of fy, okay, using what we know about logs, this would be 1 over fy times the derivative of fy, right? It's basically a chain rule for the derivative of a log. Okay, this piece here is what you're seeing right here, right? 1 over fy times this guy, right? So basically I can plug this in, since they're the same thing, I can plug this in here. Okay, when I do that, I'll have this equals negative log of fy, and then don't forget this is being squared. Okay, right? And log of fy is our log likelihood function. Okay. All right. So I've shown this relationship, right? So the second derivative of the likelihood, okay, equals the negative of the first derivative squared. Okay, so now that I've shown this relationship, I can go ahead and plug in the derivative of the likelihood with regards to theta and the second derivative of the likelihood with regards to theta. Okay, so of the log likelihood. Now this is our function, right? So what's the log likelihood, right? The log likelihood is y theta minus b theta over a phi, right? I'm just taking this and taking the log of it, right? Plus c y phi. So then when I take the first derivative of my log likelihood with regards to theta, right? This last piece will cancel out. I'll have this y here. I'll have whatever the derivative of b is, and then that a of phi will stay. Okay, and then the second derivative of my log likelihood take the derivative again, the y will go away, and I'll have the second derivative of b, and it'd still be divided by 1 over phi, or divided by a of phi, sorry. Okay, so now I can go ahead and plug these guys in. All right, let's plug this guy and this guy in down here. Okay, so I'll have, oops, let me go back. All right, the second derivative was negative b of theta divided by a of phi. Okay, and this is going to equal the first derivative, which was y, minus the first derivative of b of theta divided by a of phi. Okay, and then we need to square that. Okay, all right. Now, this first derivative of b, we showed it in the previous video. That first derivative of b is what mu is. So let's plug that in here. Negative e, and I have y minus, so this part here is mu, right? I'm going to square it. Now, a of phi doesn't have anything to do with y. So it's basically a constant. So I can actually take it out of the expected value. So I want to go ahead and do that. And it is also squared. Okay. Now this piece over here, there's no y actually involved at all. So the expected value is with regards to y. So this is all a constant. So I can actually drop the expected value because the expected value of a constant is just itself, right? Okay. All right. Now notice that the expected value of y minus mu squared, that is exactly what variance is. All right. So great. That's what I wanted to solve. I wanted to know how to find the variance. So this is equal to negative variance of y divided by a of phi squared. Okay, you can see both sides have that negative sign. So let's go ahead and multiply it by a negative and make them both positive, right? I need to get the variance of y by itself. So let's go ahead and multiply both sides by a of phi squared. One of them will cancel, and you'll still have one of them in the numerator. Looks like I meant to over d of phi squared. Okay. So still have one of these guys in the numerator. So I'll have the second derivative of b of phi, or b of theta, second derivative of b of theta with regards to theta, times a of phi, okay, and this is equal to the variance of y. Okay, so we've proved that the variance of y is going to be equal to the second derivative of b of theta times a of phi. All right, in the normal distribution, if you go back to what b is for the normal distribution, you will find that the second derivative of b is actually just going to be 1, so then your variance of y just comes out to be sigma. All right, but that's not true for some of the other distributions like gamma and Poisson.